so we are hooked up to our map sensor, which was the plan for this morning. I have to be really quick about this because I do have a customer coming. So to do this test, we actually don't want the car running, and we don't want that because we don't want our base fuel schedule. Right here. Our base fuel schedule, we don't want it to move that way, which it will when it's idling. So to see if this is going to affect things the way we want, we're going to data log, and then we're going to put the sensor into the fuel and see if it moves that way. If it does, that confirms that. It will also allow me to watch here to see if it does anything to that, which it shouldn't, because it's over there. Then we will turn the car on, then I will do it again and see if it messes with my volumetric flow ratio reading, which I don't think it should. So, excuse me. The map sensor, this sensor doesn't actually see like vacuum, high amounts of vacuum. And when I do write the final code for this, I'm going to make it so that that value doesn't actually get affected until we get over into the positive pressure range, so that it doesn't affect the lower load stuff, which is the issue that we have with the scaling in Ecutech. When you scale the map sensor for a larger one, they don't compensate for that change in the load calculations, which throws throttle control all off. It does a whole bunch of stuff, even though it's supposed to be scaling it. So we're gonna turn the ignition on, test it, turn the car on, test it, and if it works, then the next step will be to actually tune a car using flex fuel. I don't think it will be this car, only because this is a CVT and I don't want to kill a CVT. So I will have to tune this on a manual transmission car to verify everything works. Yeah. Ignition's on, turbo boost sensor reading 1.9 volts, which is to be expected. And dip this in, we should see that go up. Or not. Okay, let's look into that. It helps if the ethanol content sensor is hooked up. Let's try that again. Yep, and there it goes, up to 2.62 volts. Take it out, should return to normal. Okay, stop the data log. And you could see here that did in fact move things around. Move things around over here too. So what I'm gonna do is I'm gonna turn the data log back on. I'm gonna watch these maps so I can see exactly how this is getting affected. Okay, so it's not doing anything. So let's fire the car up and see what it does. We might need an RPM in order for it to adjust these things. We are idling. I'm gonna dip this in and see what it does. Well, it didn't do anything. Let's check this. Analyze what happened here. So here we are not in the ethanol, and then down here we are. So on the maps, we're sitting about right there and about right there. And then when we dip it into the ethanol and it changes our reading, this is staying where it is, and this moved over. Now, I have a theory that the map sensor will not affect our base fuel schedule until we are actually under load, because the base fuel schedule has a calculation in it, and it probably has some sort of load calculation in there or some sort of limiting factor. It also could just be a closed or open loop situation. But what I didn't think it was going to do was move the volumetric flow ratio, which means that pressure is being taken into account there. So it's going to be a balancing game of changing the MAF reading to move things that way without changing the boost reading that it's going to move it that way too much. But we need to get it up on the dyno, and we need to actually modify the in and the out on the dyno, and I need to do it while it's under load. So I'm going to need to write a program where I can just edit the in and the out for the map sensor, do a pull, see where it goes, pull it back, do a pull, see where it goes, and we'll have to go from there. But let me sit down and do some math as far as base fuel schedule calculation and volumetric flow ratio. Okay, so here are the equations I think they're using. I just went and found what equations are usually used. So our volumetric flow ratio with a map sensor involved, and our fuel schedule with a map sensor involved. Before, we didn't have the map sensor. So I'm assuming that at an idle, we're in closed loop as far as our fuel schedule goes, which is why our ignition timing wasn't moving around. That is going to be my working assumption, and I have a way to test that, which we'll go do in a minute. Now, if that is the case, our map directly influences our volumetric flow ratio, which is why as I increased pressure, obviously without increasing MAF, our volumetric flow ratio still increased. It shouldn't increase by much as compared to like the MAF. So basically I just had the map sensor multiplied by, I think it was an extra 35%, I think is what I have in the code. Let me double check that. Yeah, 35 to 40%, which is a pretty substantial increase. Now, if we reduce it down, then obviously that won't go down as much, because I used large adjustment values so we could see what was happening. So I'm going to change in the code to actually pull away from the map and see what it does to our volumetric flow ratio. Now, as far as fuel schedule goes, MAF is obviously a big determining factor of that. So we would have to reduce the map by even more in order to get the fuel schedule to drop even more or make it a bigger drastic change. So this is going to come down to testing, but the theory and the math behind it supports this. So I'm going to write out this equation with two different values, a high and a low map value with a standard MAF, and then I'm going to do the same thing here. I'm going to pick moderate RPM. We're going to assume a volumetric efficiency of 100%, which would be like low boost. And then I'm going to write that math out, and then we will go over what that information tells us. So did the math out, converted everything to grams per second PSI so that it's way smaller numbers, because typically you do it in PA, which makes huge numbers, as you can see by those equations. So I assumed a set MAF flow for all of these just to see what the map sensor reading would change with the pressure. So as you can see, volumetric flow ratio change and our volumetric efficiency, our fuel schedule is supposed to be fuel schedule. So ignore that. Fuel schedule change. So in theory, this should work. So I'm gonna go rev the car, hold the revs like 3,000 RPM to see if we can get it into to change from close to open or open to close loop, and see what it does on that table. Our control, we're going to log at 3,000 RPM. Okay, we're going to go put the fuel sensor in my little container here. Okay. And now we're going to rev again to 3,000. Let me analyze that data and get back to you. So here's where we're at. Our base fuel schedule changed as expected. When we dipped into the ethanol, our base fuel schedule went up by 0.2, well, 0.1 to 0.2, which at the RPM and mass airflow, that lines up with the math that we just did. The issue becomes our fuel compensation with our volumetric flow ratio. The same change in boost up drastically increased that, like drastically, which again lines up with our math. So the issue we're gonna have now is if I do the opposite and bring everything down, again, I don't wanna bring everything down while the car is running. I'd rather run rich than go lean. If I bring everything down and it dropped by that much, we're not going to get this to drop by enough to add timing to make up for the change of fuel, because the way this is going to work, and this is going to get really confusing really fast, so I'm going to do my best here. We're going to be using this map for our fuel adjustments no matter what. So when we put ethanol in it, we're just going to move over on the map. That's pretty much what we're going to do. And then by using the speed density, we're going to basically, just as an example, we're going to stop letting the car at maximum gasoline power. It won't go past like that line, which means on ethanol, we are going to move over and over, and this will basically be our ethanol fuel compensation over here. So the issue becomes we can push over and over as far as we want, and then the mass airflow we can use to move it over and over. The problem is if we pull so much map pressure out of it in order to get this to start reading that way by enough that it increases our ignition timing, are we going to be stuck in a feedback loop where I have to just increase this to decrease this, increase this, decrease this to try to get the pressures up? Fortunately, the only way I'm going to know if I'm going to have that issue is I need to tune this car. We need to actually put a car in dyno and we need to tune it. And I have a customer coming and I can't do that today. But we have seen that changing the map sensor does affect these things. We're just going to have to use the math to offset the drop in flow ratio calculations that the map sensor reduction will do. Should still work. So I need to tune this car. I'm gonna hook up a little experiment. I'm gonna put this thing on the dyno, and we're gonna see if this works. I don't want to put ethanol in this car. I don't want to have to do the whole fuel system thing. I just want to see if this theory works, and then we'll get a car that we can tune this on and actually hook up flex fuel and all that. So what I'm gonna do is we're gonna put this car on the dyno. I am going to get a second Arduino with a second output on it, one to math, one to map, and I'm going to put values in there that are fairly drastic so that we can actually visualize the change and see what it does under load. I think that's what's going to happen. And the reason I'm going to run a second Arduino is because I need to sit down and figure out running 2 of the DACs on one, and I just don't have the time to do that right now. So let's see how this goes. Okay, so in order to test this, we need actual tuning tables. So I have made this, instead of just a 1 row 10 column adjustment, now we can do it by this. And the thinking is our y-axis is our map sensor voltage, what we're actually seeing on the map sensor. So the thinking is, and these are just arbitrary values that I put in here, the thinking is everything under a certain map voltage, I want the outputs for the MAF and the map to be what they are from the sensor to make drivability better. Then I want to get into manipulation. Now, I am going to have a map sensor, a pressure sensor for speed density, hooked up to this as well. And my output to the MAF is actually going to be in speed density value. And the way I'm going to work that is basically take my pressure values and figure out at what voltage MAF reading gets me where on my load tables, and have it calculate that. I'm actually writing that math up now. That way, speed density will only be used under higher loads or over X amount of boost. I'm probably going to do over 5 pounds of boost that goes onto the speed density table. And this way we actually won't have to touch the MAF map in the car, and this is actually going to make it even easier to do speed density. So this is going to work. Next week I'm going to get a car on the dyno. I'm going to make an actual hardware kit for this that can stay in a car, and we're going to tune on speed density in E85 on a factory ECU.